Welcome friends. Let us continue to study heat engines on my YouTube channel. Kindly like, share and subscribe my YouTube channel. The topic included in today's lecture is Carnot cycle having air as a working medium, assumptions in Carnot cycle, working of Carnot cycle and efficiency of Carnot cycle. Let us see what is cycle. So it is a system which is filled up with the ideal gas. It is having some parameter, that is pressure and volume P1 and V1. Let us represent this state P1 V1 on PV diagram. So it is state number 1 and P1 V1. Now heat supply or work done takes place in the system, and the exchange of heat supply or the work done takes place between the system and surrounding, right? And due to that, it reaches to the state number 2, having the pressure and volume P2 V2. So consider it is reaches to the state number 2, having pressure P2 and volume V2. So now let us see again. The exchange of heat and work takes place between the system and surrounding, and due to that its parameter also change from P2 V2. Now it is P3 V3, and let us denote it on the PV diagram. So that is state number 3 and the parameters are P3 V3. Now let us say again some heat and work interaction takes place between system and surrounding, and due to that its parameter, that is P3 V3, now changes to P4 V4. Now let us represent it on the PV diagram. So it reaches to the state number 4, which is known as the P4 and V4. Now let us say again some heat interaction or a work interaction takes place between system and surrounding in a such a way that it reaches to its original state, that is P1 V1. So you can see here the next state obtained by the system is initial state, that is 1 and P1 V1. And it is said that the system has undergone a cycle because initial condition is 1 and final condition after passing through different processes is also the same. So how many processes the system has passed? Process number 1, process number 2, process number 3, process number 4. So after passing through the 4 processes, the system has reached to its initial condition, and it is said that the system has passed through a cycle. Now next one is the reversible cycle. If all processes are reversible processes, then the cycle is known as the reversible cycle. Now let us study the Carnot cycle. So Carnot cycle was devised by the scientist, that is the Nicholas Leonardo Sadi Carnot, in 1824. Research was related to determine the relation between heat and mechanical energy. And in that relationship, or finding out the relationship between heat and mechanical energy, the Carnot cycle was invented. It is a reversible cycle. It consists of 4 reversible processes. So Carnot cycle is made up of 4 reversible processes, and due to that it is also a reversible cycle. Carnot theorem. No cycle can be more efficient than a reversible cycle working between same temperature limits. And Carnot cycle is used to compute or compare with other cycles. Now the Carnot theorem says that no cycle can be more efficient than a reversible cycle. So consider there are number of cycles available. If one cycle is reversible cycle, another cycles are non-reversible cycle, it means the reversible cycle is the more efficient cycle and others are not efficient. Clear? And Carnot cycle is used to compare with other cycles. So it means Carnot cycle is the fundamental or ideal cycle with which the performance of other cycle is compared. Assumptions. So assumptions in Carnot cycle theorem is working medium air is ideal gas, cylinder is perfectly insulated, piston movement in the cylinder is frictionless. So we will study all these things one by one. Heat source, heat sink and adiabatic wall are perfect. And all the processes are reversible processes. So all these are the assumptions made in the Carnot cycle analysis. Now let us study Carnot cycle with air as a working medium. Now let us see, this one is a cylinder, and this cylinder is perfectly insulated so that no heat transfer takes place through the cylinder wall. This one is a piston, and movement of a piston in a cylinder is a frictionless. It means there is no heat generation between the piston and cylinder when piston moves or the reciprocates inside the cylinder. It means piston movement is frictionless. There is a heat source which is at temperature T1 or TH. There is a adiabatic wall and there is a heat sink which is at temperature T2 and TL. So these three elements of heat engine we have already studied in our previous lecture. And working medium, that is air, that is considered as an ideal gas, is filled up inside the cylinder, and the mass of that air is 1 kilogram. Let us draw the PV diagram. Initially, the state of the working medium, that is air, is at 1, and at that time pressure is P1 and volume is V1. Now we are, you can say, supplying the heat to the air. Clear? By putting the heat source in connection with the, you can say, cylinder head, and due to that, heat from the heat source is supplied to the system, that is to the working medium. And due to that, the piston moves from left hand side to right hand side. And it reaches to the middle portion of the cylinder. Let us represent it on the PV diagram. So heat is supplied and it reaches to the point number 2. At that time, the parameters are P2 and V2. And 1-2 process is known as the reversible isothermal expansion process. It means temperature during that time remains constant. Now next one is, let us exchange the heat source with the adiabatic wall, and due to that the piston continues to move from middle of the cylinder to the end point of the cylinder, but there is no heat supplied because adiabatic wall is in contact with the cylinder head. Yes, and the condition reached is the point number 3, and this process is known as the reversible adiabatic expansion process. So 2 to 3 is the reversible adiabatic expansion process, and the parameter reached are P3 and V3. Now let us see the next process. Now the adiabatic wall is removed and heat sink is placed in contact with the cylinder head. Now as it is a heat sink, the heat sink will absorb, you can say, collect all the heat from the working substance, that is mass. So heat will be rejected to the heat sink, and due to that, piston will move from right hand side to middle of the cylinder. Let us draw it on PV diagram. So that is point number 4, P4 and V4. And this process is known as the reversible isothermal compression process. And this one is the heat rejection. Now, again, the heat sink is removed and adiabatic wall is placed, and due to that, there will be no heat rejection, but the piston will continue to move from middle of the cylinder to the left hand side. And it will reach to the initial condition, that is state number 1. And That process is known as the reversible adiabatic compression process. So the four processes of Carnot cycle having working medium air are: first is the reversible isothermal expansion, reversible adiabatic expansion, then next is the reversible isothermal compression, and next one is the reversible adiabatic compression. This one is the PV diagram of the same, and this was the working of the Carnot cycle having working medium air. Now, let us draw the TS diagram, that is temperature entropy diagram. Point number 1, pressure and volume is P1, V1. Now here it is T1 because it is a high temperature, heat supplied is high temperature. And 1, 2 is the heat supplied to the system, and it is at the high temperature using the heat source. So at that temperature, T1 or TH, heat is supplied at constant temperature, and due to that, it can be denoted by the horizontal line on TS diagram, and that is the heat supplied. And at point 2, temperature is same, that is T1 or TH. Now second process is reversible adiabatic expansion, that is the isentropic expansion. Now if this is isentropic, it means entropy remains constant, then it can be denoted by the vertical line on TS diagram. So that is vertical line on TS diagram, that is reversible adiabatic expansion process. Next process is, you can say, reversible isothermal compression process. So here the next process is isothermal, means temperature remains constant and heat is rejected. Now as the temperature remains constant, it can be denoted by the horizontal line again on the TS diagram. So process 3 to 4 is the reversible isothermal compression. Heat is rejected, and that temperature is constant, that is equals to T2 or TL. That is the heat sink temperature. And what is the last process? Can anybody say? Yes, it is the reversible adiabatic compression process. Reversible adiabatic means isentropic, and as it is isentropic, it is the vertical line on TS diagram. So 4 to 1 is the reversible adiabatic compression process. And at point 1 and at point 4, entropy are same. So it is S1 is equals to S4. And at point 2 and at point 3, entropy are same. So we can say it is S2 is equals to S3. Now assumptions that we have studied are again, working medium air, that is ideal gas, we have already studied. Cylinder is perfectly insulated, that already we have studied. Piston movement in cylinder is frictionless, that is also we have studied. Heat source and heat sink and adiabatic wall are perfect. If it is not perfect, then there can be the heat transfer, right? And last one is that all processes are reversible. So all assumptions we have already studied. Clear? Now let us study the condition for cycle, because we are required to study the cycle, and cycle means initial and final condition or state should be the same. Now let us see. Expansion ratio, that is process number 1, 2, and that is given by the value V2 by V1. Compression ratio, that is process number 3 to 4, and it is given by the ratio V4 by V3. To complete the cycle, it is essential that these ratios are same. That is, if these ratios are not same, it means after 4 it will not reach to exactly 1, and cycle will not complete, and that is known as the R ratio, and it is denoted by the symbol R. So R is equals to V2 by V1, that is equals to V4 by V3. Heat supplied. Now heat is supplied during which process? Let us see. It is 1-2 process. Process number 1-2 is reversible isothermal process. Now what is the equation to find out the work done during isothermal process? Now this equation we have already studied and derived in the chapter properties of gas. Clear? So the heat supplied or heat transferred equation for isothermal process is P1 V1 ln V2 by V1. So that can be applicable here, because here heat supply takes place between isothermal process. Due to that, we have used this equation. If it is happening in constant pressure process, then we have to use the equation of constant pressure. Clear? So similarly, depending upon the process during which heat supply takes place, we have to use the equation. For here, it is isothermal process, so equation is P1 V1 ln V2 by V1. Now instead of P1 V1, we can also write MRT1 and V2 by V1 is R. Now as the mass of air is 1, so we have removed M. So it is RT1 ln R. So that is heat supplied, QS. Next one is heat rejected, QR. Now again, heat rejection takes place during which process? Process number 3 to 4. And process number 3 to 4 is again isothermal process. So we can use the same equation, PV log ln R. But PV means here it is point number 3. So we can write down P3 V3 ln V4 by V3. And here also, instead of P3 V3, we can write MRT2 because temperature is T2 and V4 by V3 is R and mass is 1 kilogram, so we can write down M is equals to 1, so it is RT2 ln R. So why it is T2, that you will come to know when you will study the TS diagram, because at point 3 temperature is T2 or TL. So now we have got the equation of QS and QR. So net work done equation that we have studied in the fundamental of prime mover and heat engine is QS minus QR. Now using this equation, let us derive the equation of net work done for Carnot cycle having air as a working medium. This is the QS and QR for the Carnot cycle. Substitute these two values here. So work done is equals to RT1 ln R minus RT2 ln R. Now which one is common here? R and ln R. So we can take it out. So R into ln R multiplied by T1 minus T2. That is the equation of work done for Carnot cycle air as a working medium. In the next, we have to derive the equation is efficiency of Carnot cycle, and that is Carnot Air Cycle. Now what is the equation of efficiency? That already we have studied in the fundamental. Yes, that was the work done divided by heat supplied. So work done equation we have already derived, R into ln R into T1 minus T2, and heat supplied is RT1 ln R. So putting that value, now which terms can be cancelled? R cancelled, ln R cancelled. So the answer is efficiency of Carnot cycle air is T1 minus T2 divided by T1. And it can be written as 1 minus T2 by T1, or it can be written as 1 minus TL by TH. So this is the efficiency of Carnot cycle air. Now let us study again assumptions. Working medium, air is ideal gas, cylinder is perfectly insulated, piston movement in cylinder is frictionless, heat source, heat sink and adiabatic wall are perfect, and all processes are reversible. Considering all assumptions, we have derived the equation for efficiency of Carnot cycle air. And it depends upon only two temperatures. One is heat source temperature and another one is the heat sink temperature. Now what are the limitations? So what are the assumptions are the limitations? Let us see. What was the assumptions if you will say working medium air is ideal gas and cylinder is perfectly insulated? Now this again becomes the limitation. What is the limitation? Working medium is not perfectly ideal gas. And second one is there is some heat loss from the cylinder. Now what are the next two you can say assumptions? Piston movement in cylinder is frictionless and heat source and heat sinks are perfect. So these are now limitations. There exists friction between piston and cylinder, and heat source, heat sink and adiabatic wall are not perfect. And last one is all processes are reversible. That is my assumption. So what is the limitation? In actual practice, no processes are reversible. So if you know the assumptions clearly, you can write down the limitations easily. For your queries, kindly comment in the YouTube channel comment box. Kindly like, share and subscribe my YouTube channel. Thank you.